Okay, so starting from today, we're going to start to talk about the new subject, which is natural language processing. For many years, actually, text is the more important data format than pictures. Okay, for many years that when I was a student, which was many years ago in the university, we didn't even have graphics. We didn't even have Windows. Okay, at the time that everything was simply just text. Okay, we write programs, which is going to be in some language. Some of you might have heard of Fortran, COBOL, BASIC. Have you heard of a language called Pascal? Okay, those are the older languages. And at that time, that everything that we're trying to do is to do computations like for mathematics and also for, probably trying to, in the field which is closer to AI, actually people are trying to do theorem proving, okay, reasoning. So those are all about text. And so if you remember when we started to talk about AI, the first question posed by this great scientist, Alan Turing, is Turing test. And if you remember the question asking a Turing test is that when you have conversation with a being behind the wall, can you tell by just talking to that particular being? Can you tell whether it's a person or is a computer? If you cannot tell it's a person or is a computer, then that computer is a successful, what we call as artificial intelligence. Okay. So if you look at the Turing test, it has no mentioning of vision, no mentioning of image, no mentioning of graphics. Okay. So graphics actually is later when we started to have more powerful computers, then we have the Windows system, then we have started to have, all different kind of a screen and all different kind of computer games. Okay, then when the graphics, okay, all the pictures, all the vision becomes to be something that people are more used to. And of course that with the invention of smartphones, people are now, even when you are really sending text short messages, you're still using the window or your smartphone. Okay, and a lot of time now, I don't know whether you remember that there was a kind of a machine, old machine called BlackBerry, okay, which text-based only, but nowadays, of course, that when you use your short message system, you can still send pictures, but that was not the case. Okay, in the past, actually, that when I was a student, we sent emails, and in our email, we couldn't include any pictures. Okay, so so from humans' point of view, human intelligence point of view, okay, computer vision, the computer vision is something built in for us, okay, for most of us, but we know that some people actually, they are blind. Okay, so they cannot see anything, but still they can have conversation. They can have intelligence by learning, from people, speaking to people to learning from different things. Okay, so, but for a long time in the field of AI, natural language processing has been a very difficult job, and it has not made too much progress. And people almost have given up doing research on natural language processing. Okay, not until probably after we have this, a lot of computing power, and then we have this deep learning, and then we have the large language models, and we have ChatGPT, and now everybody said, oh, okay, language actually is something that we want our computer to be able to do, okay, rather than just computer vision. But computer vision, the first wave of success of AI actually is on computer vision, not on natural language processing. Natural language processing, the success of natural language processing probably started around 2020 maybe, okay, because you know that ChatGPT was invented, was released in 2022, okay, and so after that, of course, now everything evolved. And so still, in any case, in terms of AI, the foundation of the AI used to be there are many different things, but of course we think that deep learning is something that is the most important technology. That's why we started in this class. We started with deep learning, a lot of theories, and we teach the software and this and that, and then we have covered computer vision, okay, and now we're going to cover natural language processing, okay. And so the slide I'm going to use, part of the slide for today is going to be by this Professor Lin, Yinjia Lin, in our department. He will be offering a natural language processing course next semester, okay, in the spring. But he will offer the natural language processing course in Chinese, and that will be the course for the master's student and the undergraduate students, okay? But there will be another professor, Professor Gu, also she will be offering natural language processing, okay? And that will be in English, okay? So you will be taught, will be taken by the master's student and the PhD students, okay? So for those of you who are, want to take the English version, okay, then you should take the course from Professor Gu. But for those of you who are more comfortable with the Chinese teaching, then you may want to take the course from Professor Lin. Okay, so both will be covering natural language processing, and that will be the whole content of the course. But in this class, we are introduction, so therefore I'm going to spend 3 or 4 weeks, at least 4 weeks, I think, okay, on this topic of natural language processing. And today we're going to talk about the basic concept, okay, and how is that going to be different from computer vision for the deep learning, okay. And next time we're going to talk the large language model, and the week after, okay, we're going to cover the subject of RAG, retrieval augmented G generation, I think, okay. So the RAG is going to be, I will I'll invite someone to come to teach RAG, and RAG is going to be the topic for our next homework, which is going to be our last homework. Okay, so we're going to be talking about the foundations today and then the next week, but on the week after that, we're going to talk about RAG, okay, and the week after that, we're going to talk about all different type of large language models and applications on natural language processing. Okay, so natural language processing, okay, it's actually now is a very popular topic, and there are many universities has offered the courses. And again, I'm using the material which is you can find it online from this link, which is the sorry, let me hold on a second. Okay. Need to do this. I want to. Okay. So it's by Professor Jurafsky. So he is one of the very well-known person in this area, and he has written a textbook. Okay, he has been teaching this course also, and so the website actually, if you go there, then you can find the book. Okay, which is the January 2025 version, which is very new. It's available. It's a draft version available, but he also on the website it has all the course contents of the material, and we're going to be using a lot of the slide from his course. Okay, so before we talk about the large language model, okay, these are the kind of things that people have been working on for many years for natural language processing, okay? And I used the word classical natural language NLP task. It doesn't mean that those problems are no longer important, but those are, some of them are still very important, some of them are not so popular anymore, okay? The first thing, you can see that some of them are kind of similar to like video, okay? Classification. Text classification and computer vision, we also have the image or the object classification, okay? Both are trying to, from a, kind of a content of something, okay? Either is a picture or is an article or is a report, okay? We'll try to analyze what it's about, okay? So the most important now, of course, is the sentiment analysis. Sentiment analysis usually is something that when you buy something from the e-commerce website, and usually they will ask you to say, do you want to say something about using this particular product, okay? And so this sentiment analysis is for them, for the computer to try to see that when a user gives some feedback about a product, what is their experience, and are their experiences, are they, when they have something to say, is that a good thing or is it a bad thing, okay? Or sometimes that when you have a conversation with your friend, or if you receive some conversation, some comment from your friend or something, okay, when they give you something, can you just by reading the text, reading the something, can you make a decision that whether they're saying something good or something bad about you, okay? In our normal conversation, of course, that we often have conversation with our friends, okay? And but sometimes that when you talk to some people, you don't know whether they are agreeing with you or they don't agree with you, okay? They usually are so polite, and especially if you speak to Japanese, and they are very polite, okay? They will be, agreeing with you, and they'll say yes, 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 but actually they are not agreeing with you, okay? They will say, oh yeah, you're right. And they will say, but, okay, then they start to say something, okay? So the sentiment analysis actually is not always so easy, okay? Not always. It's many, it's very hidden, okay? And so this is also related to, in terms of the natural language inference, that how do you, from something people have said, can you inference, okay? Can you try to derive from what they have said into something that you can make a conclusion, okay? Because sometimes they don't give you a conclusion, but they want you to make the conclusion yourself, okay? So, maybe that, say, for example, suppose you said that, oh, you go talk to some friends and say, let's go to have lunch. Okay, they say, oh, okay, nice. Okay, then you start to say, where should we go? And people start to say this and that. Okay, and then they talk about this restaurant. Should we go to this restaurant? And they will make some comment. And they will say, oh, how about this restaurant? They will make some comment. Okay, but they never really give you a definite answer to say, I think we should go to this restaurant. Okay, but maybe from the conversation after you have talked for a long time, then you finally figure out, finally understand, finally you can make some sense from the conversation and decide to say, oh, actually, they want to have some, maybe something, for example, like a Western, okay, maybe they want to have something, not pasta, maybe not pizza, but they want to have something and this and that. And that would be something called the natural language inference. Okay, so natural language inference definitely is much harder than the sentiment analysis, which is just trying to decide whether something somebody said is good or bad. Text generation is another thing which is different from what we are talking about now in the generative AI. Okay, but there are some similarity. For example, text generation, for many years, people have tried to do machine translation. Okay, I'm sure that some of you have tried to use some older machine translator device. Okay, you can buy some such device and you speak in one language, and that language is supposed to be translated. Those are the older generations of the machine translator, okay, which is different, very different from the generative AI now, okay. But this was the hot topic. Summarization also is something that people, right now people are doing. That when you give a big text, an article or a lot of report, can they try to find out what's inside of those report and give a short conclusion or short summarization of the result. Dialog generation, this is something that in the old days when they study Turing machine, okay, or trying to, beat the Turing test, they already are trying to study how to have some conversation. An older generation of the dialog generation is that they can create a software. Whenever you say something, they try to take part of your language and then speak it back to you. To say, are you saying this? And you say this, do you mean this? Okay, they're just kind of repeating always what you said. Okay, so just like they are having a conversation, just like with some of the human beings also. And when you talk to some people, you say something and they say, oh yeah, but they never really quite agree with you, or they don't agree with you. Okay, but those some of the strategy has been used in the older the AI things. Okay, sequence tagging. Okay, this is something that is to say that it's similar to classification, but it's more of like trying to identify, okay, in some long speech or in some long conversation, okay, can you mark to say that, okay, this is the part which is important, okay? So many times that when you have long speeches, okay, and you want somebody to highlight it for you, to highlight it for you is a little bit different from summarization. Highlight it for you is really just tagging to say, okay, you should pay attention now. And I think this is always very useful in my teaching. Whenever I talk about something, and when I use a keyword, what I'm going to talk about next is going to be in the final exam. And everybody will start thinking, oh, okay, now I need to listen. Okay, if I say with something, okay, this is something that we're going to have the next homework on this, then everybody says, okay, that is the part that the speech you should pay attention to, right? Okay, so that's the tagging. So tagging is a little bit different from summary. Tagging is just simply to say that in terms of important. And tagging also is different from classification. Classification is trying to have the whole thing, then try to make a decision to say that whether it's good or bad, whether it's right or wrong. But tagging is not making any judgment, but tagging just trying to show something is important. Okay. Name entity recognition. Okay, this is a little bit different, similar to classification. Again, it's just trying to say, okay, in this conversation, in this text or in this article, okay, can you somehow recognize something, okay, and which maybe you can match this and that, okay, and eventually that will fit together, okay. Word segmentation. This is something a little bit related to what we're trying to talk about today. Is how do you actually divide the word into something so that you can understand the word, okay? Because the word could have, kind of different parts, and sometimes we don't understand the word, but if you understand part of it and you can put it together, then you can understand the meaning, okay? For those of you who don't know Chinese, then you probably, cannot really see Chinese as a picture. But for those of us who know Chinese, actually Chinese is very easy to understand. When you see a word, you have never seen it before, but you can divide it into components, okay? And some of the components will give you the hint what this is about, okay? Usually, whenever you talk about something which is the name of a fish, then you have a component which says this is fish. Then the second part here would either give you the sound of the fish or give you the type of fish or give you something, okay? If you have something which is on the side is like this, okay, it usually means it's human. Okay, then the other side or the other parts, okay, of the word would describe something which is probably related to human, behavior, human, component, human, whatever supposed to be used by human. Okay, so word segmentation is trying to divide the word into different individuals. Okay, just like if you replace this one segmentation from word, you replace this one here by image or vision, then you understand what is the image segmentation, right? We'll have this picture. I want to show which part is a dog, which part is a cat, and things. Okay. Finally, we also have the text matching. Okay, so the text matching is trying to understand, okay, something that is not just syntax, but it's a semantic. Okay, you can have text matching, which is something that, of course, that many of you know already. That whenever you submit a paper, okay, usually they try to detect to see that whether your paper is your original work or have you copied, okay, from some other papers. Okay, so they can use this text match. The text matching doesn't have to be word by word, but they can compare the similarities, okay, of two different articles. And if the paper you're submitting to a conference for public publication, to a journal for publication, they'll try to check to see that your article or your report is that semantically or textually similar to something that somebody else has written before. Okay. This is also very used quite often whenever people want to see that whether the program you have written is your own work or not. This is very important for computer science professors because we often give homeworks. Okay, and in the past when we give homeworks, many of the students actually they will work together and they'll submit different program, but actually they are the same program. Okay, and they think that they can trick us by changing the variable name, by changing some of the structure, by changing this and that. Okay, but for us that we can either visualize it, okay, or we can use some software which can actually report to say that these two students' work or their program actually they are the same copy. Okay, even though they look different. Retrieval. Okay, retrieval is something that, of course, that we also now doing now is that from the a whole bunch of text, can you somehow just give keywords, and the keyword will be able to find all the related content about that keyword, and then retrieve that for you, just like similar to the search engine. Okay, so all this are. You can see that many of them are still ongoing work, but many of them are now easily solved by a large language model. Okay, so let's just try to have another overview of what exactly is natural language processing. Okay, not just the what we want to do, but how we can do it. Okay, so to do the natural language processing, we can think about, come back to look at this computer vision. Okay, when we try to image processing. So for image processing is that we have some pictures. Okay, and then with the pictures, we would put them into the computer. Originally, the picture would be maybe in the format of some JPEG or maybe in the raw pixels. Okay, but we need to first convert a picture in human world is a picture, but we need to somehow move that into the computer so the computer can understand this actually is a picture. Okay, if I understand, I don't mean that to try to do the feature yet, but simply to be able to store this picture in the computer. Okay, so even for pictures, we know that there are many different formats. Okay, you can have just raw pixels, which will be just the matrix of each of these pixels, and each pixel would have the RGB, and each RGB has 0 to 25. Or we can have that in the JPEG. We can have that in the PNG. We can have this in the PDF. Okay, so there are many different type of format you can have. Okay, to store them in the computer. But after you have put that in the computer, then whenever we want to do the machine learning, okay, then we need to have different algorithm to extract the features, okay, either in this histogram, or we can do the convolution, okay, so that we can understand what's inside of this picture in a certain way, in a more abstract way, not in terms of just the picture's pixel, but in some abstract way, okay? And until this day, whenever we do the CNN, we don't really know what is in the, kind of before you do the fully connected layer, okay, you generate some feature or some embedded space, but we don't really care what exactly is in there, but we just want to know that some information or some knowledge has been learned from the picture, okay, so that you can use that to try to make some prediction to do something, okay? And so we need to do all this training. So the same thing, whenever you have a text, okay, or you have some article, you have some information, okay, then, or that is what we usually say, we have a corpus, okay? The corpus means that you have a whole collection of things in text that you want to process, okay? So the first thing, of course, you still need to do is to somehow to be able to store all this collection of natural language into the computer, okay? And to store that into the computer, we will talk about today, okay? There are different type of coding, there will be different kind of vocabulary, there will be different kind of segmentation, there will be different kind of representation. And some of them, okay, you can store them in a way which is, you can use them, but they are not so efficient. And when we are trying to do large language models, we are trying to process a lot of information from our human world. So therefore, the way that we store the information from the raw corpus is going to be very important, because that is going to have a direct, kind of in terms of the complexity, in terms of the size of the information, it's going to be greatly affected by the way that you can use to encode that. Okay, so the first thing we need to do whenever we do the natural language processing is that we need to find a way to be able to represent the information that we want to process. Okay, so after that, okay, then so today, or maybe today, or maybe next week, we'll be talking about different type of what we call as word embedding. So our for each language, we have article, then we have a sequence of word or sequence of something, okay, or characters or something, and we want to be able to save them in our computer, and that the information that is being put into our computer, we want it to be something already have some useful representation. Okay, first is the size, and secondly is going to be about something about the semantics. Okay, so when we look at the picture again, when we show this picture of cat, when you do your homework, what do you do to process the picture? Okay, when right now we give you a picture, whenever we have a project, okay, we say this is going to be a 224 by 224, or this is going to be 15 by 15. Okay, we are actually just saying that, okay, the raw data is always going to be just in some pixels. Okay, we can do that too with our natural language processing. Okay, but again, we try to make the meaning of the information that is stored before our machine learning is already something which is meaningful, not just some sequence of characters. Okay, and that's why that people have started to study the idea of the embedding, so that we don't store the raw information, we don't store the original the characters or your writings or something, but we can store them in some format which are already in certain format, in certain coding, or in certain structure that can already give us some meaning. Okay, and this is what we call as word embedding. That we don't want to store the raw word, okay, but we want to put them in some format that will be easier for the computer to be able to use that for machine learning. And one of the most popular is the word to vec, okay? So after you do this, your original word will be converted into vectors, okay? So each word actually is not going to be just this alphabet, okay? Apple is no longer going to be just APPLE, but it's going to be some dimension of vectors, okay? The vectors of some dimension, okay? And in most of the large language models, this vector actually is very large, okay? It's a very large dimension. Say, for example, it could be, 300, size of the dimension size of the vector, okay? So you would say, well, that's actually silly, right? Because here, actually, I have the apple, which is only 5 characters. But you are now going to convert it into something which is represented by 300 numbers. So you are actually increasing the information. You are not really reducing the information, okay? But you were talking about efficiency. So what do you mean by that? Well, the idea here is that, yes, I can store them just APPLE or banana, BANANA. But when I try to use them, then I need to do many processing in order for me to try to understand an apple is an apple, a banana is a banana. But if I can put them into some encoding, into some vector, then if the vector is already having some meaning, okay, then it will be much easier for me to be using them to try to make some further processing according to our specific task that we want to do. Okay, so which is just like saying that here, converting the word or character, word, okay, or vocabulary into vectors is similar to like from the picture to do the convolutions into eventually you can have this flat, kind of a vector, okay? And from the fact vector, then you can try to say, I'm going to do the classification, I can try to do segmentation, I can do something. You can try to do many different things in here. And as we said, when we have the CNN network, usually the part here is something that we just mechanically, after we have trained the model, we just mechanically process them. And so the picture actually will be converted into also is a vector. Okay, so every picture will be a sequence of vectors here before they do the fully connected the processing the layers. Okay, the same thing is in the natural language processing. Before we started to even do many of these tasks, if we can convert somehow the words, okay, into these vectors, then it will be much easier for the later jobs, okay, to be able to perform the operation. Okay, and so from the word embedding, for example, that suppose we use the something like the word to vec, okay, then you will see that each of the word in some language, okay, say for example this is in English, okay, you will see that we can put each of this word here in some vector space, okay, and in the vector space, the word, even though they are separate words, okay, but they will be able to be formatted in such a way that, say for example, when you say find the distance between China to Beijing, okay, and Japan to Tokyo, okay, and also Poland to Warsaw, and this and that, okay. If we build these vectors right, okay, then from China, if you go the same way in the vector space, then for you to find the Beijing, then when you go to use from Japan, you can try to travel in the same direction. Then you will be able to find the word Tokyo, okay, because that particular distance, that particular direction, that particular kind of path is for you to find where is the capital of that particular country. Okay, so if we can put all words, all vocabulary into such a space, okay, using some embedding, then we already can capture some meaning, not behind these simple alphabets, not just simple behind some character, but we can already understand something in the real world, okay, the meaning of each of the word, okay. So which is to say that from the text processing, when we are trying to process text, okay, we can think of the text would have two different labels. One is a syntax, the other one is semantics. Syntax is just how it is been written, how it is been presented, but for each word, actually, there are some meaning, there are some information behind it, okay? And when we use the embedding, we are trying to put that kind of idea together so that we'll be able to put each of this word, not just in terms of its syntax, but its semantics, okay? So Beijing itself is going to be relationship to China is the capital of that, okay? For Russia is Moscow, and for Turkey is Ankara. And so that kind of structure, that kind of relationship between words is something very important for many of the tasks, especially for human to try to understand some sentences or some articles and something. Okay, and so word embedding actually is an important step for us to be able to do many of the natural language processing work. Okay, there are different ways people try to do word embedding, and we'll just give some very high level overview, but we'll come back to visit this later today or next week. The word embedding is that how you represent each word in some vector space, okay, in some format, okay, and so the problem is that, okay, the number of words that we could have, number of vocabularies we could have in a specific language or specific domain, it could be very, very big, okay? And so when we try to convert them into some vectors, okay, quite often we're going to be able to process all the information from some original, kind of input data set, okay? In the input data set for each one of them, we'll be able to find some particular vector representation. But we know that in many languages, okay, the total number of vocabulary is just so huge. And in many of the articles or many of the data that you have, you probably will not be able to cover everything, okay, that existed, okay, in that particular language, okay. So one of the things that we're going to have to handle is that even though we have learned to try to convert the word into vectors for many of the words, there is a possibility somehow next time we're going to see some new word that we have never seen before, okay? And when you have never seen this word before, can you somehow come up with its representation in the embedded space? If you cannot, then you cannot process it. So you need to have some way to say, even this word, I have never seen it before. Can I somehow convert them into some embedded, okay, so that I will be able to ask my machine learning program or ask my AI to process it, okay? So that is something that we need to do, okay? For each word, whether we have seen it or not, okay, we need to have some way to be able to find it's embedded. Do we have that problem in the pictures, in the computer vision? When we do the computer vision CV, do we have such idea of vocabulary? We don't, okay, because each picture for us, okay, even though semantically we'll try to identify there are some ears, there are some eyes, there are some nose and furs and this and that. But when we take a picture, okay, we always just say, okay, the picture is a collection of some information, okay, and then we will try to have our convolution layers to be able to identify whatever we can identify. But there are always going to be something that we may not be able to identify, okay, but still we will need to be able to make some decisions, make some predictions about something that we can see from the picture. Okay, so in the computer vision, different that we are not always capturing all patterns or features. Okay, but still, okay, we are trying to be able to say, for those features we can detect using our convolution network, we can try to make some decision. But for computer, the natural language processing, okay, we probably have kind of a similar thing that, okay, we have never seen this word before, okay, but somehow we need to have our embedding algorithm to be able to say, yeah, I have never seen this word before, but I still can guess what it should be, okay, in this particular vector space, okay. So using the idea from here is that, okay, if when I represented all of this, okay, into something, okay, and probably, in the information I have collected before, maybe there's a country, okay, let's just use some very, very simple example. There's a country called Palau. How many of you have been to Palau? Do you know where Palau is? For people in Taiwan? Palau, Borneo. How many of you have been there? So maybe in an article that you will see, oh, okay, there's something called Palau. Okay, now suppose that you don't know anything about Palau, you have never seen it. Okay, how do you put that in this particular space? Okay, and now what we can say is that suppose I know Palau is supposed to be a country, then I can put it to be something like in here. Okay, close to in the all of this. Okay, or Palau, we know that actually Palau is a small island next to Philippines. Okay, so for people in Philippines that they probably would know that, oh, this is actually a place close to us, so they would say, okay, where is Philippines, and then I'll put this to be close to them. Okay, so we can always use some approximation, okay, to try to identify what is going to be the vector representing that. Okay, so machine learning is always something that we're trying to always try to process something. We don't always process something we have learned, so we try to process something we have never seen, okay? And for text, we also need to do that, okay? We'll talk about this algorithm later in the class, okay? But basically, that they design some ways for us to be able to try to find ways to identify how do I actually present each of the word, okay? To have the encoding to build the tokenization, okay? So in the large language model, in many of the natural language processing, okay, nowadays, we don't use each word as a unit of processing, okay, but usually we try to use subword, okay, or we now use a fancy word called token. So whenever you use the ChatGPT, okay, they don't measure how much information you are processing, but by word, but they tell you how many tokens that you have, kind of submitted, or their answer that give you so many tokens. Tokens, okay, most of the time is part of the word. Okay, each word could be divided into several tokens. Okay, but sometimes also that it's possible that we have some tokens actually will be combining several words. If the tokens actually could be capturing the concept multiple words together, then a token actually could be bigger than a word. Okay, but the idea of a token is that each of the token actually is some concept. Okay, and there will be many different ways for us to be able to come up with the idea of token. Okay, but in the current large language model, they use different. They use kind of a comparable token algorithm to be able to convert the text into tokens. Okay, and so that they when they do the natural language processing, they will be using the tokens. Okay. The other thing is the important thing is that we want to be able to process the natural language similar to like when we try to do the computer image. Okay, the computer image usually what we do is that we have some pictures, then we have some labels, then we say, okay, now I'm going to ask you to try to train your network so that when next time when I give you a picture like this, you will be able to predict me what is going to be the label. Okay, what is the object which is in the picture? Okay, we have, I think we have briefly mentioned about self-supervised learning. Okay, which is actually not to use some label data, but simply use a lot of information to try to train the network and without labeling the data set, individually. Okay. In natural language processing, a lot of time we are trying to use the self-supervised training from the large data set, and which is what we call the pre-training, which is simply to say collect a lot of information. Okay, you don't need to do the training, but those large collection of set of data that we will be able to try to automatically try to use our algorithm, try to understand structure, try to capture some information. Okay, once we have captured the information, then we can already have some understanding about the information. Okay, then after that, then for the specific task you're trying to do, then we can try to use a super training, okay, by giving it some data set with the labels, with the specific answers that you try to find out, okay. And this is the general way for many of the large language model to be able to do, because that when they are trying to process the information, which is a large language model, which is a whole bunch of information, which is billions of text data, it is impossible for us to try to label each one of them to say, oh, this one here is the meaning of this particular place is about something. But we just try to collect from the information and try to use some self-supervised learning so that we'll be able to, that the system learn by itself. Then after we have this general knowledge, then we can try to do some fine-tuning, similar to the fine-tuning in the computer vision, which is to say that you already trained the network, which you can already recognize something, but then we give you some new data set, and this new data set would have some specific labels I want you to predict out of this new data, input data, okay? And fine-tuning here in the large language model can be the same thing. After I train the pre-train the model, okay, then I can start to have human to talk to it, okay, and then let the system to figure out what's going on, okay. We will mention a little bit about the RNN. We also, mention about the transformer, because the information that we're going to process now is not going to be just individual bit. It's going to be individual pixels, okay? But it's going to be a sequence of words or tokens, okay? So when you try to process a sequence of things, okay, the way for you to process the sequence needs to have a new structure, which is different from just a convolution. Convolution allows us to be looking at things in a two-dimensional way. Okay, when we do the convolution, then we look at 2x2 or 4x4, use a 2x2 filter, 4x4, or even 11x11. But when we have a sequence of text or information, okay, then we need to have some way to be processing them one after another, okay, and then we cannot restrict it to say that we just have 4 words, we just have 5 words, okay. We want to be able to train the model which can continuously take in the input, and when you are taking the input, somehow you can find the information from its neighbors to be able to figure out what's the specific meaning of certain thing. So for example, suppose you have some word to say, open a bank account, and another sentence says, on the river bank. Then you should be able to tell that from the surrounding words or context, the bank in this first one is different from the bank in the second one, because the first one here, open a bank account, the bank here means that it's an institution for you to be storing money. But on the river bank here, this bank here means it's a location which is the side of the river. And so we want to be able to design some algorithm that we can try to process the information one by one, and then we can find out exactly what's going on, okay, about certain word, about certain things from all its neighbors. And so therefore we need to have all the idea of our neighbors, okay, even though the neighbors concept also has been used in the convolution, but the convolution usually is more restricted in a certain area. But we'll have the large language model. We're going to try to have much longer sequence. Okay, so we'll be talking about all these different. Eventually, we talk about all these different large language model, which I'm sure that many of you have heard of BERT, and many of you have heard of GPT. Okay, and BERT is trying to be able to encode the information, and GPT is trying to be able to generate the next word after you have a long sequence of the information collected. Okay, and also we will cover ChatGPT, which is to try to make the GPT to be able to talk to human and to have some answer which is similar to what human is doing. Okay, and so in addition to just pre-training, fine-tuning, also it is able to try to make the result to be more human-like. Okay, just like it's a conversation from human beings. Okay, so this is this in this first lecture, I just try to give you an overview. What is the natural language processing? Okay, and there are many different components, and we will take a short break, and then we'll start talk about all the details. Okay, so let's take a break. Even though it is an old discipline, it's actually the science has been around for many years, but of course we know that the impact or the power of AI was not really understood, okay, or appreciated until kind of they maybe in the past 15 to 20 years. Okay, you can see that we have already seen this picture, ImageNet. Okay, the competition starting from 2012 when the AnexNet was designed, was starting to use the by introducing the computational neural network, is that when the classification error has dropped to be quite small, okay, and to be even better than human, not until like 2015, 2016. So the deep neural network, especially in the later ones, that when we have all of this processing, okay, the number of the people or the models using GPU actually has grown quite a bit. Around 2012, that there was only 4 teams that used the GPU, but in 2013 it's 60 teams, and 2014 is 110. Okay, and which also makes the performance of the things to be dropping quite quickly. Now, of course, that for the natural language processing, the power is also growing. After from 2017, that when we started experiencing all this computer process computer image, then they have also been used to do the natural language processing and cause the right now with the large language model, which is actually very, very powerful. Okay. So you think about the computing power needs for computer vision and text processing. Which one do you think is going to be higher? Natural language processing and computer vision. Which one is more difficult to do? More difficult in terms of the required computing power. I think it should be obvious now that natural language processing actually is requiring more computing power. Why is that? The amount of information that we need to process, okay, in order for us to have a good AI system for natural language processing is much bigger than comparing with computer vision. Okay, when you compare with the computer vision, yes, we are doing this computer ImageNet. How much data is will be there in the ImageNet? How many pictures? Millions, right? In the order of millions. Okay, but in terms of the natural language processing, we're trying to build all these big models. How much information are we using to build the large language model? Billions. Okay, billions. Because when you think about human intelligence or human knowledge, are there more knowledge in the text or are there more knowledge in the picture? It's definitely say that probably will be in the text, okay? Because for us, say for example, okay, for human, for our conversation, do you use text to communicate more or do you use picture to communicate more? We talk every day, we listen to things every day, right? Even though that we watch TV every day also, watch YouTube and watch this and that. But most of the time, since we were, born, you were taught as a kid, you're always talking and listening and you're trying to have a conversation with your friends, okay? Yes, you play TV games, but you don't play TV games 24 hours a day, okay? Sometimes you play TV game. Yes, sometimes you take pictures, okay? But the amount of information that been captured in pictures, okay? At least that we have collected, okay, compared with the text, okay? The knowledge, the depth of the knowledge in the text still going to be much bigger than the image, okay? How is our world is going to evolve in terms of computer technology? Is it going to be evolving more around the computer vision, or is it? Do you think that the text processing or the language processing going to be more important? How do you see that in the future? Your communication, okay, or people's humans communication, is it going to be more text based or is it going to be more picture based? I think this is a big question that nobody knows, okay, because the world is evolving so fast. There was a time that remember the company Facebook changed the name to what? Meta, right? When Facebook changed the name to Meta, what's the reason for it to make a change? Because Facebook believes in the future, more communication is going to be in the form of vision. Okay, that's why they built this, the Facebook, machine. I don't remember what they call it now, the goggle or whatever. Okay, but they think that okay, many things that we in the future is probably won't be going to be in the immersive world. Okay, rather than in just text and things. Okay, so yes, they do have the Facebook, but now they are seeing more and more people are trying to use the picture to communicate. Okay, and you can see that this is the case also in the. How many of you have the use IG? I mean, I'm sure that you all watch IG, right? Instagram, right? Do you like to watch Instagram or do you read Instagram, to your friends more, or do you talk to your friend more? Or some friend that you are not, kind of living close to you? Okay, let me change the question again. Okay, when you have some friend, okay, you don't talk with all the time, you don't communicate with all the time. Okay, if you read their writing or you see their Instagram, their IG, which way do you think would present you more information faster for you to kind of know your friend or know what they are doing or what they are thinking? Is it writing or is it picture? In Chinese, we have saying is that, well, not Chinese, but there's a saying in general that picture is more than 1,000 words, right? So a picture actually is can capture a lot of information. Okay, whether it's a high resolution picture or low resolution picture, a picture can actually present a lot of information. Okay, but still, right now, that most of our computer vision task is trying to be able to understand the picture, but it's not really, kind of making the pictures or computer vision to be a very interactive way yet. Okay, but I think that's going to happen. Okay, just like in the past when we have the natural language processing, okay, they are just trying to understand what's in the writing, but not until the generative AI becomes so powerful or so successful that people started to feel that, oh, okay, actually AI can do a lot of things. Okay, but how many of you have used generative AI to produce pictures, new pictures? AI can do that, right? You can teach AI to say, okay, I want you to draw something, I want you to put this, I want you to put that. But is it easy to control yet? But is it easy for you to talk to AI, in terms of ChatGPT? Do you know how to talk to ChatGPT? You know, right? So to somehow to talk to ChatGPT, okay, in terms of text, we don't really need a lot of training because it's just like talking to human, and we are more used to be talking to human, okay? But to be able to use picture to be presenting our thought or our things, okay, this is something that we still don't know. I mean, most people don't have that kind of skill. Okay, in the future, whether we're going to be able to have, you can just imagine that this is probably in some science fiction. Okay, in the future, when you talk to some people, each of you would have something, and you show them a picture, they will throw you back a picture. And you show another picture, they show you another picture. Do you think there would be a better way of communication? Would it be more efficient for communication? Okay, I'm just trying to have some conversation, and I'm trying to see that how do you compare between the text and the computer vision? Okay, and both are very important AI technology. Okay, and even though that there was a time that computer vision actually is a very, very powerful, everybody's doing that, and now everybody's doing text natural language processing. Okay, and also there are some models right now they can both process both the text and picture. Okay, but for human, we are able to understand picture much better than for us to be producing pictures. Okay, but for text, we can both understand text and also for most people, okay, to be able to say something naturally. Okay, so until the day that we are all trained to be able to express our thinking or our idea or our whatever in picture, it's going to be difficult for us to try to communicate using purely pictures. But I think using pictures to communicate actually is more efficient than using text. Do you agree? You can see a picture in 1 second, then you understand what's going on. But it may take you many, many different sentences for you to describe the situation, right? And that's why that when software like Instagram is so powerful, because that they just need to, your friend or somebody just need to show a picture, then everybody can get, what they are doing, or what they are what they like, and this and that. Okay, and so but anyway, we have now had many different deep learning models, and some of them are designed for text, some of them are designed for computer vision. But now, of course, that with ChatGPT now, everybody is so crazy about the large language model. And of course, that it's not just the ChatGPT is not just to process text, but also to be able to generate text. Okay, and I don't know whether you understand that in the large language model, actually there are 2 or 3 different type of large language model, which we'll cover a little bit later on. But here I just want to give you some idea. Some of them are actually designed for encoding. Some of them are usually designed for decoding. Okay, and some of them actually are doing both the encoding and decoding together. Okay, encoding is to be able to process the information so that it becomes to be inside of some model. Okay, so that the model actually has a lot of knowledge about, a lot of intelligence about whatever input data they have received for training. Okay, and these are usually the foundation of many of our current popular language model. The current popular language model, for example, like GPT or like ChatGPT or Cloud and all these things, they are designed to be able to generate output. Okay, and this is usually what we call decoding, because they usually need to have some model which they have trained. Once you have the model, then you can ask questions, and then they can try to produce something from the information that has been decoded. Okay, they have been encoded, so that they can decode your question into the things that they have already inside of their knowledge base. Okay, so actually that there are many different type of this. Say for example, instruct GPT, and we have the GPT-4, and then we have all these different type of GPT. Okay, all the different kind of generative AI. But generative AI actually is just part of this the whole group. Okay, some of them they are using the information from some encoding in order for them to be developing different kind of ways for them to be able to generate output, or to generate the predictions. Okay, so we will come back to talk about the large language model later in the semester, probably 3 weeks or 4 weeks from now, and then we'll be trying to compare with all this compare all these different models in our discussion. Okay, this is the slide which I will leave this for you to look at yourself if you are interested. It's a short. I think it's BBC video talking about, is AI the future of the healthcare? Is trying to answer that question. Okay. So now I'm going to start to go into some more theoretical foundation of text processing. So we have started to say that, okay, when we have a large text input data, okay, there will be a collection of things, okay? And of course that for us to understand the content, we usually, in our each different language, we have the concept of words, okay? And so a word, okay, is something when we try to learn a text, we need to learn what the meaning of each of this word, okay? And then we try to how to put it together, okay? And then we try to, because of their sequence of the word presented as well as the format presented, then we try to capture the ideas behind a sentence, okay? So, so this is, you know, if you don't think about this as a information, but think of this just a sequence of text, okay? Then you can count to see that how many words are here, and you can see that we can, you know, individually count to say, oh, you know, this is a piece of information that has 16 words, okay? But 16 words here, you know, sometimes that we count or sometimes we do not count the punctuation, okay? You have the count punctuation, then there will be 18 punctuation, okay? But sometimes when I have a sequence of the information, okay, or text, the number of words is not always the same as the amount of information that you have, okay? So for example, suppose somebody is, you know, not speaking, you know, kind of very fluently, okay, they will utter, okay? And so they will, maybe their speech will be in this form. I do many business data processing. So their language actually, you know, would have many things. Some of them are not very meaningful, and some of them are just repetitions, okay? They are fragments and they are this and that, okay? And so from the AI's point of view, okay, when I have a piece of information or when I have some input data set, I first need to decide what is going to be the unit of things I'm going to try to use that to put inside of my system so that I can treat it to be my input data set, okay? And that's the study is trying to do here in the first step of the text processing, okay? So here we have something, okay, which is a typical sentence, okay? And in any kind of language or in kind of some background information, okay, we will have sequence of words, okay? But the sequence of words, we can usually, you know, put them into two different things. One is going to be called the type of it, and the other one the instance of it, okay? Type is an element of the vocabulary, okay? And you know, the amount of the number of different type of words in here, and the instance, usually the instance here is going to be bigger than types, okay? So I don't want you to think about this to be meaning of it, okay? Let's just look at this just like, okay, this is something that you don't understand what kind of language it is, okay? But I can simply try to count to see that how many different words are there, okay? And how many different type of them they are there, okay? And for for people who are studying text, okay, or natural language processing, they first need to decide that how do we consider something to be the same with TH8EW, okay, THEY and THEY here with capital or lowercase, okay, are they supposed to be the same? Okay, and so for people who don't understand this language, they will say, well, this one here with the capital T and lowercase t, they are different because they look different. Okay, so if you give a new language, you would think this is different. Okay, but of course that if we understand the language, then we say, oh, actually they're the same word. Okay, but they are just been used, put in different places in a sentence, so therefore that they are presented in a different format. Okay, And you also have something like this, I am, okay? And I am here, is it considered to be one word or is it considered to be two words, okay? And grammatically, we know that this one here means actually I am, so they should be presented as two words, okay? But in many of the, if you just process them directly, okay, in a particular language, you may think this is one word because they are actually together. There's no space in between, okay? So depending on the language you're in the process, okay, each language may have different format, different ways of putting either alphabets or characters or something together, okay? Not every written language has spaces. And now, because we're trying to build AI and the AI can be used by all different languages, we are going to need to try to come up with a way for us to be able to collect the information from all these different languages together. Okay, so we need to be able to process Chinese, we will be able to process Japanese, we need to be able to process different Thai language or other things. Okay, and so for example, okay, so when we try to process English, then we can use the word, the concept of word, and the word is a sequence of characters collected together and it has some meaning. Okay, but when you try to handle the Chinese, actually we have characters, or you can say this is also some kind of alphabets. Okay, as I said that each of the Chinese character actually is a combination of different components, and different components actually together would make some meaning of it. Okay, and so what is important in when you process a natural language is not just to look at the syntax, but also we are going to try to understand the meaning behind some characters or behind some words. Okay, and so in the people who study linguistics, they have a name which is called morpheme. Okay, morpheme. This is to try to say each of the word or character, okay, actually probably have some collection of meanings together, okay, and which make it to be one word, okay. Each word, on average, okay, in our, the English language, you usually have an average of 2.4 such meaning in there, okay? And so by deciding what counts to be a word is complex and not always agree. Okay, so here is the reason why we're talking about this is that when we have one sentence, okay, what is important is not so much of how many words, but what are the different things together to make that concept of that particular sentence, okay, or to make the meaning of make the purpose of that particular sentence. So what is more important for the machine learning is really not to break it up into words, but actually to understand all the individual meanings together, okay, or morphemes together, so that they can understand the whole thing as a collection of your concept, okay. And so here is when we have a Chinese sentence like this, Yao Ming 进入总决赛, Yao Ming reached the final in the basketball game, okay, in the NBA finals, okay. How do you break this one up into tokens? So if you look at this, how many characters are there? 7, right? So if you want to try to encode this in your AI, should it be 7 different concepts or 7 different ideas in there? Or should it be something less? Here you can see 1, 2, 3, 4, 5. In terms of English, actually it's 5 words. So 5 words and 7 characters. how do we actually encode it in the AI? Because AI should be multilingual, right? You speak in the Chinese, speak in the English, you speak in Spanish, you speak in different language, but the same idea. Yao Ming has reached the final, in the MBA. Okay, that particular sentence here. How do you break it up? So even for Chinese, okay, there are different ways for people to decide to break it up. Okay, depending on who you're talking to. Okay, this is one study in Chinese tree bank. You decide to break this one into 3 different concepts. Okay, or morphemes. Yao Ming is one. That's just that particular person. Okay, reach or 进入, which is to reach. Okay, it enters. Okay, that means that particular achievement or action. Finals means that's the actually the final games in the NBA. Okay, so 3 concepts. But you can also break it up into 5. Okay, Yao and Ming, because one is the last name, the other one the first name. Okay, so they can break it into 2 different things. Reach, okay, is 1. The finals, okay, there are 2 different kind of final. It could be just the last final 4. It could be the final 8. It could be the final, semi-final. It could be the real final. Okay, so the finals here, okay, they decided to say, okay, it should be broken into 2. Because in the Chinese character here is actually not talking about finals, but actually talking about overall final, the last final. Okay, which is different from just to say finals. Okay, so in this in this combination here, it's going to be 5 different morphemes. Okay, 5 different concepts. Okay, or you can just like each character, you can break them up into individual ones because each one of them actually is a character. It is its meaning. Okay, and the whole sentence together, of course, is trying to capture something, some event. But on the other hand, Yao is the last name, Ming is the first name. Enter is actually 2 different actions in Chinese character, but actually it's one concept. So you can break them into each of different ones. Okay, so how do we choose tokens in Chinese? Suppose you enter this one here into your ChatGPT or into your something. The ChatGPT or the engine, okay, needs to first decide how to break this one up into tokens. Okay, the way that they broke them into different tokens would actually affect how they process it. Okay, how they capture the knowledge, how they're actually able to try to make some difference. Because here you can see that if I have this to say just finals, and then if I here says that it's actually the overall finals, there are actually 2 different facts. One is to say you have entered the last final, and the other one say you are in the finals. Could be the final 8, could be the final 4, could be final 16. Okay, so by taking these 3 into 1, you are missing some of the fact that actually is actually the last final. Okay, but keeping the name Yao Ming is meaningful to because this is referring to that person. Okay, but on the other hand, you break them up into 2 different ones. One the last name, the other one first name. Allow you to be later on to say, well, actually, maybe sometime that this makes a mistake. This person's name is spelling incorrect. Okay, so if you break them into 2 different things, then the first name and last name. So even the last name is messed up, or the first name is messed up, the idea still will be captured. Somebody with name Yao and has entered the finals. So this looks like it's easy. Okay, looks like it's not important. It's not so kind of something. But actually, when you try to design a computer AI program, that actually is important. Okay, so again, coming back to look at this picture, when you try to design a computer vision, build a computer vision AI, okay, what do you decide? You decide to say which architecture I'm going to use, right? Because right now that you can select different architecture. In different architecture, what do they make the difference? What are the differences between different architecture? In the deep learning, number of layers. Okay, number of layers, and maybe sometimes that they have different residual or not, and this and that. Okay, but the number of layers also talk about the number of filters that you are going to try to learn. Okay, and so you can think of say that each different architecture in the computer vision is trying to learn different details. Okay, which is similar to like when you have a sentence here, how much detail do you want to learn from this particular sentence? Do you just want to learn these three, ideas here, Yao Ming, riches, finals, or do you want to, and kind of collect the information that there's a person with last name Yao and last first name Min, and then this and that. Okay, so those looks like kind of a very different decisions, but they could eventually affect how your system is able to provide the detailed answer or to be able to differentiate between different kind of things. Okay, and so in most of the time when we are trying to build a computer natural language processing model, we don't always say that how many type of words, okay, how many type of words are in a particular language, but we would say that how many different type of words are in a particular data set, okay, because for different data set, okay, they would have different type of, those, even though all of these are different English, okay, but you can see that, the type of words used in Shakespeare's writing, in the Brown corpus, in all of this, okay, even though they're English, the different type of words are still different, okay? And of course, in terms of instance, how many different times they've been used in them, they're different, okay? So roughly, of course, that the bigger the corpora, which is the bigger the amount of information, then there will be more kind of a different type of concept, different type of words. Okay, they will be adopted. Okay, so for people who study linguistics, they usually they can find out to say that, okay, given you a particular some reports or some article, the number of words or number of instances you have is n. The type of words inside that is probably n to the beta. Okay, and the beta usually is about 0.5, which means that the type of words you use in some writing is usually the square root of some, some collection of the information. Okay, so that's just to give you some idea that the size of the information and the type of the information, these are two different concepts. Okay, type of information is going to be something that we need to be able to encode in our system so that we can differentiate between different concepts, different morphemes. Okay, and so the larger the data set you have, okay, the more information you'll be collecting, but the basic unit of the information that you need to capture, okay, or the basic unit you need to define is going to be about the square root of that. Okay, when we're talking about embedding, we are trying to convert something into a vector space. Do we convert this or do we convert into this? Okay, let me ask the question again. The question is that when we try to build an embedded space for some particular language or some in particular input data set, okay, when I design my embedded space, okay, how many different type of embedded space I need to have? Is it going to be this or is it going to be that? it's going to be this. Okay, so just like when we're talking about English, how many alphabets do we have? 26 or 52? Because you have uppercase and lowercase, right? Okay, and then you may have some punctuation. Okay, you have comma, you have period, and this and that. So we have actually total of maybe about 100 or something. Okay, which is the number of type of information that you would use. But in terms of English report, it could be thousands of words. Okay, and so therefore the amount of information that you're presenting is usually much bigger than this. But this is what is more important for people who are trying to design how to embed them. Okay, and so so when we try to find an embedded space to be able to encode this information, okay, we need to understand that, okay, NLP system usually doesn't use word, but actually they use small words, small unit, which is called subwords, okay, because that we usually will try to break the words into something which is capture some concept or morphemes, okay, and the morphemes, say for example, suppose you have fox, okay, which is one word, okay, but actually it's just one idea, which is animal. Cats, actually we have two morphemes because cat and with an S, it captures two concepts. One is that animal called cat, but with an S actually means that there are many cats together. Okay, so the morphemes, okay, is for us to be able to design. So when you want to design the embedding for English, would you design the embedding for cats, the vectors, or do you design the cat? Do you need to design the cat and cats? Suppose you're trying to create this embedded space. You have all these vectors, right? Do I need to have one vector for cat and another vector for cats? The answer should be no, okay? Because this is going to be one unit, and there will be another unit called S, and this will actually be together, okay, to capture that particular word actually has two tokens, cat and S, to mean that, okay, it's actually, so there will be one vector, okay, which is representing the cat. There will be one vector representing the fox, okay, and there will be some information in there. And so for morphing, okay, for us to be starting embedding, actually, the idea of morphing, okay, is more important than the actual word, okay, and or you can say that morphing defines a subword, okay. Here is yet another example from this. It's a little bit interesting because this is the lecture notes from Stanford University by this professor, American professor, but they always like to use the Chinese as a discussion for the morphing. Okay, so here is to say that this is a long sentence. Okay, for those of you who understand Chinese, this is about recipe. Okay, how do you actually process something? It's a plum dry vegetable. Use clear water to soak soft. Remove out after, drip dry, chop fragrant. Okay, meaning that English meaning is soak the preserved vegetable in the water until it is soft. Remove, drain, and then chop the vegetable. Okay, but you can see this is the Chinese writing of that. Okay, and the question now is that how do we define the morphing out of this? How do you define the morphing out of this? How many tokens should you use to represent this and this? Now they're the same. Okay. In Chinese, okay, actually, the first one, 梅干菜, or the plum dry vegetable. Actually, this one here should be one, right? Because it's one specific morpheme. It's a little bit different from this when you say this is the preserved vegetable. But the preserved vegetable doesn't mean that. Preserved vegetable just means that all kind of vegetables which are preserved, but actually this one here in the Chinese writing, actually this should be just one, just like Yao Ming is one person, and this particular vegetable should be one. Okay, so to identify the morpheme, okay, in a particular language or particular thing, okay, it's not so easy, but usually there are some general rules. Okay, first we will try to find out what is the central idea and what is the ethics. Okay, which is they say when you have work with the ed, okay, then we say this one here should be ethics. Okay, which means that it is something to on top of the original concept. Okay, but it actually add extra either tens or the number of things or this and that. Okay, but when you define the specific morpheme or specific unit for you to do the embedding, it should be 2 instead of 1. Okay, and this 2 here, actually, only this work here is the important concept. It should have a unique vector space. Okay, the ED here, the ES here, actually, they are going to be in the language. Also important for the fact, in terms of the vector space, okay, it doesn't need to have very unique space. It's just a concept which is adding on the additional meaning into the original root. Okay, so basically that if we want to design the token, okay, or design the individual morpheme for each language, okay, we need to understand that different language actually have different, let me use the word density of the morphemes. Okay, some languages, okay, they have each word can capture many, many different meanings. Okay, already included many different meanings or many different semantics in there. But in some language, okay, it's supposed to be more straightforward. Okay, I don't know if this is true for people from Vietnam. It doesn't mean that your language is easier, but it just means that each word which is broken, okay, usually already captures one specific meaning in there. Okay, and English is about 1.7. So in general, that when we say English one word, on average, you capture about 1.7 different concepts inside of it. Okay. Could you give me an English word with the 3 concepts in there? Can you think of any English one word, but it has 3 concepts in there? This is just a joke. CGU. What is CGU? Chang'an University. One English word, CGU, but actually there's a concept of university, the Chang, and there's in Chang'an, of course, you can say this is one name, okay, but actually it's 2 different characters, okay, 2 different words. But in English, I can write it to be CGU, okay, and you can think of other examples, okay. Basketball. Basketball. Should it be 1 token or it should be 2 tokens? Basketball, okay, of course that is made of 2 words, right? Basket and ball. But when you want to encode it in your language, or do you think it should be 1 or should be 2? I think probably it should be 1, because if you break it into 2, then when you say you play basketball, then you just like you're playing basket and you're playing ball. But actually, you're not playing basket and playing ball, right? You're playing basketball is one thing. It's that particular kind of ball. The particular kind of ball should be 1. Okay, so so the sub-word concept or the more morpheme concept, okay, is not always just syntax. Okay, let's take a break and then we'll go even something even lower level. Okay, let's take a break. Understand the concept of word and the morpheme, the word and the subword and the idea of a token. Okay, and now we're going to start to think about, say, how do we actually put all this information inside of a computer? Okay, and to store the information inside the computer, we know that we need to make it to be numbers. Okay, digital numbers. The digital numbers are because in our most of our language that we have writings. Okay, we have alphabets, and English has English writing, Chinese has Chinese writing, but the important thing is that they all need to be encoded in some way inside the computer. Okay, so the first thing human did when we designed the computer is to first to try to translate something from the English character to be something which the computer can understand. Okay, and the first set of standard which has been defined is called ASCII code. ASCII code, we probably all know that means that each English alphabet, okay, would have one specific code, which is 7 bits, okay, can be used to represent that particular word. So, say for example, like you have A to be 61, okay, or which is a hexadecimal number, or A to be 97, okay, and B is 98, okay, and C is 99. And you also have the some code for the punctuation, and also you have the capital A is 41 or 65, the decimal number, and B is 66 and such. And so therefore, when you have an English say hello, then we can type that in on our keyboard, and that information will be translated into this sequence of numbers 68, 65, 66, 60, 6C, 6E, 6F, okay, inside of the computer. And then when we get it, then it will be encoded, okay. Now, of course, we also understand that because now we are trying to deal with multiple languages, and so therefore many different languages, so therefore ASCII code with only 128, 27 combinations is not good enough, and so it has been expanded into the Unicode. And Unicode is a way so that we'll be able to represent almost any kind of characters around the world of different languages, including Chinese, Arabic, Hindi, and such and such. Okay, and so therefore now the English character is part of that. But in addition to that, it can store more than 150,000 different kind of characters. So that's the first step. Okay, whenever you have a language, okay, whenever you have something, we can store that inside of the computer. Okay, but just to store that inside the computer, okay, it means that you can be taking a lot of space, because for us to be able to store this information, we need to have so many bytes, okay, and which means that a lot of time that you are going to be storing some information, okay, that is not meaningful for other languages. And also there are some of these alphabets or some characters are not very often used. Okay, so in most of the files that we use these days, we use UTF-8. So UTF-8 is try to get rid of a lot of this not so popular language characters, or not so much of get rid of, but to represent it in such a way that not everybody needs to take the same space, because that if you have uh, 4 bytes for every character, okay, or every alphabet in any language, then you're going to have a lot of zeros, okay, and which make that the system to be not so efficient, okay. So because originally you only need to have 6, 8, okay, to be representing one thing, but you need to have 3 extra bytes to be storing the information, and those information are wasted. And so UTF is to try to create a format so that the code itself can be 1 or 2 or 3 or 4 bytes. Okay, usually it's 2 or 3 or 4 bytes. Okay, and by using the initial heading, okay, then we can decide to see that, okay, if the first bit is 0, then it's going to be 1 byte. But the first 3 bits is 0, then it's going to be 2 bytes, and then first 3 bits with some combination. Okay, you can use some combinations of the first few bits to decide that that particular character needs to have so many bytes for you to encode the information. Okay, in this way, the coding for any text from any language will not have a lot of zero bytes in the system. Okay, and so most of the 127, okay, which is 1 byte, is going to be ASCII code, okay, but the other script those characters in European and Middle Eastern and African will be 2 bytes. Chinese and Japanese and Korean characters will be 3 bytes, and then the rest of them will be 4 bytes. So there won't be so many such 4 bytes information. Okay, if you have a lot of more Western text, you will take only 1 or 2 bytes to be able to encode each particular character. But whenever you have the Asian language like Chinese, Japanese character, then they will start with 3 bytes to be taking the space to encode 1 character. Okay, so that allows to have more efficient, okay, fewer bytes to be able to carry common characters, okay, and also that if a file is corrupted, then we can try to identify the sequence, okay, and then to repair the information using some techniques called self-synchronizing. Okay. UTF-8 is now used in most of the format for storing information internationally. Okay. So from that, we can start to think about, say, well, if we can use this encoding idea to be reducing the amount of bytes to be able to keep the information, then we can also try to design some way for us to be, kind of tokenized, okay, to be able to try to reduce the amount of information for us to be storing the morphing means, okay, and one way to do that is to use kind of try to understand the meaning of something and try to see that whether you will be able to easily kind of put things together, okay, using what we call as a byte-pair encoding, okay, for us to do the tokenization. So let me just quickly show you some example, and then it probably can capture the idea more quickly. So suppose originally we have A, B, C, D, E to be the type of kind of information that we want to encode. Okay, and we can try to look at the amount of information, okay, that we have, okay, or the input data set we have, and see that we can define any pattern, okay, they appear. So if you have a corpus, you have some input data set, which is like in this particular sequence, okay, so we know that definitely, you have 5 types of information. Okay, you have A, B, D, C, A, you can see that A, B, C, D, E, they are in there. But then we can try to see that which are quite often together. Okay, so here you can see that whenever we have A, it most likely will be followed by B. You have A followed by B, you have A will be followed by B. So it will be useful for you to be creating another new alphabet, AB, so that your original information, text, doesn't need to have so much space anymore, but you can use this new alphabet here to capture A and B now are together in this sequence here, and then you have others information. So by creating this new alphabet, you can reduce the original amount of information from 6 here to 3, while the other 4 are kept the same. Okay, so by doing this bi-pair encoding, so you can try to find all information that appear, and they quite often they will appear together. Okay, then create a new alphabet for that, and then just use one encoding for that. Okay, then you can kind of create your own new character or new coding. Okay, and then you can reduce the amount of information that you use to store the information. So here you can see that after we have done this, then you can do it again. And you can see that in here, in this, the C and AB are often together. So therefore, you can now combine the C and AB together into a new alphabet called CAB. So this CAB now will have its own alphabet, but in the original sequence, which is going to take a total of 10 different storage locations, now can be represented by 1, 2, 3, 4, 5 different locations. Okay, so they will make this encoding to be more efficient. Okay, the total amount of information is still the same. You still have this whole sequence of this thing, but now you will be taking only half of the space. Okay, so by using this idea, we can try to create different tokens. Okay, so the create these tokens here, okay, this is not based on any other information. This is based on the information that there are some information that will be repeated often. Okay, and so therefore you can create new vocabulary, but the vocabulary is for you to be creating a different type of coding, but in terms of actual amount of space for you to be storing that piece of knowledge or this piece of input information is going to be smaller. Okay, and so if you can do it this way, the total number of storage space that you use to store anything that you receive as an input can be reduced. Okay, and can be reduced quite a bit. Okay, and this is something that we can use to try to, one way for us to be creating tokens, okay, which are actually, they are combinations, some original simple tokens, okay? And this is something used quite often for different ways for us to be creating tokens, okay? So here you can see that in some GPT-4.0 token, okay? The tokens actually, they are not always going with the word, nor it is going with the character, okay? Because in the normal coding, we'll be using character for our UTF-8, but when GPT-4 takes the input sequence like this, then you would try to create, you would be using token, which actually will be already capturing some of this together, okay? And to create a special way for us to say, oh, flowers here, this is a spatial pattern I've seen quite often, okay? And I will create a token for that. Okay, anyhow will be one token. And here, anyhow, you can see it's using 2 different tokens because one token is capitalized and the other one is not. This is different from this one here, okay? So the number of tokens, okay, can be selected to be able to encode some piece of information, okay, so that we'll be able to not to be using UTF, because UTF is character by character, but we can try to create tokens and each of them capture some concept, okay? And then we also can use the idea of the BPE to be able to shorten, if some concept or some things are often come together, then we don't need to always keep them separate. We can use BPE to be reducing the number of to increase the vocabulary, but we can reduce the amount of information. Okay, and so okay, so here it says that even though the BPE tokenize is multilingual, and training is still usually by English. So therefore that most BPE tokens used for English and leave less for the other languages. Okay, words for other language usually they're just split up. Okay, so here you can see it shows a the result of a token. Okay, tokenizer, which actually for English is actually quite efficient. It's actually able to from this in this sentence here, you'll be converted into 18 tokens. But if this is the whole sentence is written in Spanish, then you're required to have 33 tokens. Okay, so the number of tokens is going to be different for different language. Okay, so in the system is going to run differently. Okay, so the token, the way for us to be designing this BPE is going to be based on the information that you receive. Okay, information you receive. Okay, and that can be used to try to summarize. Okay, what is quite often been stated or been presented in that particular the information. Okay, and for people who study linguistics, okay, they often want to not understand that the information which is the corpora has some different, context information, like who are the writer, what time, what variety, what language, what a specific function, because each of these may affect how you would be using the token or not. Okay, to create some token which is maybe different from others. Okay. Okay. So that is what I want to talk about, the basics. Okay, and now we're going to go into more details of the another one, which is the let me see. Okay, we're to back. Okay, so far we have talked about this tokenizer. Okay, in the concept of syntax, we're talking about each word will be combined of some characters, and characters, they may appear together, and characters could be in one language or another. Okay, but what we really want to capture in our machine learning a lot of time is the meaning, is the semantics. Okay, so we want to be able to understand the semantics, okay, in the language or in some information, because the semantics actually is going to be the knowledge that we try to capture. Okay, by reading something, we could just like say, for example, suppose that you learn some Korean language, okay, or just like the Latin. Okay, you can read by looking at the language. You can read it, but you don't understand what's going on. Okay, because that the language give you the sound, but the giving doesn't give you any hint what it's supposed to be. Okay, so in our machine learning, usually we want to be able to understand, okay, the meaning of each word, okay, and then the meaning of the words together, then we can try to try to understand the knowledge or the intelligence behind it. So the text classification method we have seen so far, they are really looking at just strings. Okay, they are really just specific combinations of characters. Okay, so if you ask a question, say if I have something called DOG, okay, the system will understand this is a combination of DOG 3 characters. And if I say this is going to be DOE, what is the difference between DOG and DOE? It doesn't mean anything to the machine learning, okay, because DOE is DOE, DOG is DOG. They don't have any relationship. It just means that they have two characters are the same and they have one character is different. One is G, the other is E, okay? So we want to be able to say we don't really need to have a dictionary for us to try to understand the meaning, but we can somehow use our way of encoding, then we'll be able to say, for each word, okay, that we have, or for each token we have, okay, we can try to find out what's the meaning behind it, okay. So the word mouse, okay, in English, it can be referring to rodent, to animal, or we all know that the mouse can be a device that is controlling our computer, okay. So simply the word mouse, if it shows by itself, we don't really know what it's supposed to mean, okay, because it could be either two. So there are many words in different languages, okay. They are actually, one word may have different meanings, but they are also different words. They have the same or similar meaning, okay. So you can see that here we have some of these words. They are shown together: couch and sofa, big or large, automobile or car, okay, and the water and H2O, okay. So these are the synonyms that we use quite often, okay. But how do we actually, try to capture the idea? And something which also a little bit different is similar. Okay, so they are referring to things which are similar, but they are not exactly the same. Car and bicycle, cow and horse, they are similar in some usage, okay, but they are not exactly the same, okay. But for some purpose, they will be the same, okay. Cow and horse, both are animals and both are domestic. But car and bicycle, okay, they are for transportation, but they are of course quite different size, okay? And here you can see that, people have done some study here, say, for example, like vanish and disappear. These two has a very high similarity, 9.8. Behave and obey, definitely not so similar, 7.3. Believe and impression, 5.95. So you can see that, in our vocabulary or in our types, okay, there are words. Some of them, they are similar, but they are to different degrees, okay? So for people who used to be studied linguistics, they spend a lot of time to try to understand, say, for example, what are the different things and how do we actually put them together, okay? And you take a lot of effort to try to understand every one of them, and also try to understand the relationship. Houses, the door and roof and kitchen and family and bed, okay? And the restaurant, we have the waiter and the menu and plate and food and menu and the chef, okay? So all these are buildings, but they are different meanings in there, okay? And so there are many different type of ways for us to be studying the relationship between different concept of different, between words, okay? Um, and this used to be all done by human, okay? And human has spent a lot of time to be defining this, and until this day, you can still go to look at some dictionary. If you type a word on the web and go to dictionary, and dictionary will give you all this to say that, oh, what words are similar to this and that, okay? It's actually a lot of work, okay? So, but again, we're not trying to ask our machine learning to be copying everything from the dictionary or to look at the dictionary, okay? So we want to be able to find a way to say that we want to capture some semantics. And we capture the semantics in our coding already. Okay, so when we are given certain word, somehow we are able to somehow put those words and put a coding so that the encoding of the word, okay, already can tell us something about the meaning of that, okay? And one, I think one very important foundation for the natural language processing in machine learning is to actually come up with this vector semantics, okay, to create the structure of storing the information in vectors, okay, and that vector actually is not just the sequence of numbers, but actually can capture some semantics, okay? So this is now becoming to be something, of course, everybody probably had heard of, okay? But the vector semantics is something that in the past, people have not done this, okay? Because people look at each word to be an individual concept, and maybe you have different subword have different concept. But in machine learning, we quite a lot time we rely on this concept. The meaning of a word is used in the language. Okay, when we use a word, okay, we don't need to understand the word, the semantics of the word, but we can look at its neighbors, okay, and then we can see that what is the meaning of that, okay. So the usage is defined by its environment, okay, or the usage defined by the words around them. So if we look at one word and we look at the words around them or close to them or next to them, okay, then we can try to see that they are something meaningful or not. So a statement has been made. The statement has been made here is that if A and B has almost identical environments, then we say that they are synonyms. If you use two words always almost in the same way in all different situations, then we can say that these two words probably have the same meaning. Okay, so I'm going to show you this one here. Okay, this one here is quite interesting. Let's read this. Okay, suppose that you try to understand what is this oncho. So here it says that, okay, we have already seen such a sentence. Oncho is a delicious sauté with garlic. Oncho is a superb over rice. Oncho is leaves, oncho leaves with salty sauces. Okay, and you see from some other part of the input, it says Spanish sauté with garlic over rice. Okay, chard stem from and leaves are delicious, and then collard greens and other salty leaves greens. So if you have seen both such three sentences and this in our inputs, okay, then we can probably make the conclusion to say that, well, onchoy is the description of onchoy here and the Spanish description here, they are almost the same. Okay, so we can probably say onchoy is probably like Spanish. Okay, we also see that onchoy here is something can be done over rice. And this is similar to this one here, okay? And onchoy has some salty sauce, okay? And this one here is some salty sauce. Then we can probably conclude from this sentences and this similar sentences to conclude to say that onchoy is probably some leafy green, like Spanish because it's like here, and also could be like chard, okay, or could be like collard greens, okay, because people are using them in a similar way. Okay, so we have two different words. We don't know what it means, but if these two words are always kind of being used in a similar way, okay, then we can kind of conclude to say that these two words, they are probably, have similar semantics. Okay, so the answer for this question, what is onchoy? This is onchoy. Okay, and this is Cantonese. Okay, so anyway, so you can probably do the same thing to try to understand what is kangkong. Okay, or you can try to understand what is this if they will be used in some writings to be in the same way, in the same description. So the semantics of one word, okay, or water Spanish, okay, or 空心菜 in the Chinese, okay, we don't really need to look up something, but we can just try to find out the information from our original text. And if their text, they have a description and they're used in a similar way, then we know these two probably have similar semantics, okay? And they will give us the definition now. We can define the meaning, okay, not by looking up something, but by simply looking at the distribution. We can define the meaning of a word by its distribution and language use, meaning that it's neighboring words. We can define the meaning of something by its neighbors, okay, and or some grammatical environment, okay. So that allows us now to have the vehicle to be able to say, I'm going to go from your input and I'm going to try to find out what's the meaning of a word, okay. The other idea is that I can try to find out that, you know, in terms of the meaning, okay, and how often they are used, okay, and then, you know, how much, you know, if we describe them, some word in some dimension, okay, some words to describe it, how, you know, balance, okay, the pleasantness, okay, we can define the intensity of the emotion, we can define the degree of control, okay, so we can give the score in each of this dimension, okay, to describe some concept, okay, and that particular number, the set of numbers, will be able to give us, defines the meaning of some word, okay. And so these two ideas, okay, it's been used in our machine learning now, is that, okay, we are not going to try to look up the semantics of each word or each token by the dictionary, but we're going to try to define the meaning by the distribution from its input data, okay. And the second thing is that we're going to try to define the meaning, okay, not by some, you know, kind of complex thing, but we simply can try to use some multi-dimensional space, okay, multi-dimensional space. And so in that way, we can try to set up a dimensional space. Then that dimension is going to be defined by, you know, certain way. Then for each word, okay, that we have in our vocabulary or in something, then it will be put in some particular location, okay? And the specific location of a word in that particular multi-dimension is going to be based on its similarity to other words, okay? And that similarity is going to be depending on its distribution. And the other thing is going to be based on some of the information that we can collect about that specific dimension, okay? And that is how we come up with this idea of the embedding, okay? Embedding that we are going to try to use the machine learning to try to look at from the original input data, find out from the original input data about each specific context of certain word or subword and how it is used in all the context, and also how different are they in terms of multiple different dimensions, okay? And this is the way for us to be showing that we can now try to encode a word as a vector, okay? In that way, we can encode a word as a vector, and that vector will be a sequence of numbers, okay? And then the sequence of numbers, then we can use that to store the information inside of our computer. Then we'll be able to try to understand that. So in most of the machine learning, NLP software now, we don't use just UTF. We don't just use ASCII code. but we use tokens. Okay, and the tokens is not just simple embedding, but tokens actually are being processed so that the tokens actually will be able to include some information about the meaning, include the information about something. Okay, and one of the most popular one to use is called word2vec. Okay, word2vec is to create such embedding. Okay, so that whenever you speak, input some input sentence, the input sentence will be encoded into these tokens, and the tokens, each of the token actually will have some specific vector, and that particular vector actually is not random vector, but actually some meaningful information. So comparing to the computer vision, okay, we are now processing text. We are not processing image. Image will process them into pixels. The pixels will be numbers, okay? Pixels, however, after we process the pixels by the convolution, it will be a sequence of the embeddings. Now, when we have text, we'll process the text. We'll try to match each of the text, okay, and also its surrounding into some particular vector. And that particular vector, will be a sequence of vectors, and that sequence of vectors actually will already have some semantics meaning in there. So that's how we process natural language processing, because natural language processing already are not giving us just the random pixels of pictures, but already is given a sequence of meaningful semantic subwords. Okay, that is a very important part of the natural language processing. When I give you a natural language sentence, you'll be converted, you'll be embedded into a sequence of code, but the code is not just random code. The code already has some meaning in there. Okay, already have a sequence of concept in there. And the sequence of concept, later on, when we talk about transformer, when we talk about machine learning, those concepts will be used to try to check to see that in a sentence, okay, this concept and that concept, how related they are. And they will be used to create the idea of attention. Okay, so attention is not a mechanical thing. Attention actually is you need to have this word2vec, which will give you the semantics. And from the semantics of each individual word, when I have a sentence, I can understand how semantics are the same or different from each word. And then I will be able to find out what is important to be able to try to decide that, what are the things that can be used to capture the concept. Okay. Okay. So word2vec is something that we're going to spend a little bit more time talking about. Okay, even though it's just mathematics, but this is going to be the most important foundation for us to do the encoding. Okay, from some random text into something which is a sequence of meaningful tokens. And the sequence of tokens is not a random sequence. That sequence tokens actually, because they already have some semantics in there. And later on, we'll say, okay, we're trying to do the machine learning. Okay, it's quite different from saying that we're processing just the random bits, but it's going to be more like we are already have in the middle of this, our convolution layers, because the earlier one have already learned some patterns in the convolution. So you are already here. You are not here. Okay, when you have converted them into tokens, you are already here. You already know what's around in that sentence, and that sentence is referring to some particular countries, particular concept, particular person. Okay, and then from there we'll try to use more concept or mechanism or tool to find out the relationship between them. Okay, and that will be the idea of the attention. And the idea of attention will allow us to be able to later try to make the system to be able to understand, and then also to be able to generate outputs from the inputs. Okay, I think that's all the time we have for today. So we're going to stop here, and next time we're going to try to go into the bigger system concept. Okay, using the idea of the word2vec. Okay, Thank you.